Hello, everyone. Welcome to another of the Research Software Engineering seminars. So this week we've got Boris Bolliet from the Kavli Institute down at the Institute of Astronomy. So I think a lot of your background has been in astronomy and cosmology, but recently you've been looking more at kind of the use of agentic AI, sort of multi-agent-based systems, and particularly at where that can be used in scientific research. And so I thought it'd be an interesting sort of research software seminar to hear a bit about that and maybe what's happening in the research space of this. So yeah, welcome, Boris, and please do tell us.
Yeah, great. Thanks a lot. So yeah, indeed, since roughly a year, I decided to completely refocus my research from cosmological data analysis to agentic artificial intelligence. And what I'm interested in is the question of autonomous scientific discovery and this grand vision of self-driving laboratories. So in a very recent talk by Andrew Ng, he highlighted this new area of opportunities here. So mentioning that even though a lot of attention is on AI technology, especially foundation models, like the GPT language models or those from other places like Anthropic or Meta, most of the opportunities are going to be in building AI applications. So the applications I'm interested in is what these are going to mean for research in science, and in particular in cosmology. So in cosmology, we are dealing with huge data sets. So as you can see here on this slightly outdated slide, I think these numbers for the industry were from 2017. But the sort of data volume that you see here from Facebook is actually smaller by quite a bit than the data flow and volume that we will have to deal with the square kilometer array. Great. So this is the square kilometer array here on the top right. And this pointer is, yeah, okay. And here at the bottom is the Atacama Cosmology Telescope, which is the main telescope with which I am involved, and I've been involved in my research for the last 5 years or so. So cosmological simulations, as many of you, I'm sure, know, are some of the drivers for the largest supercomputers in the world. So they involve exascale computing nowadays. And for instance, the simulation that I'm going to show now very briefly was one of the highlights of this Frontier supercomputer. So this is a sort of image or illustration of what we do with these cosmological simulations. In terms of data volumes, they represent the same sort of volume as our observational data set. So we have to solve here very complex differential equations for millions of particles, of dark matter particles. And the goal of this particular simulation is to try to understand how dark matter interacts gravitationally to form the large-scale structure in the universe that we are trying to observe with our telescopes. So as you may, so this is another snapshot of a state-of-the-art simulation, Illustris TNG. And you see here maybe some patterns that look more or less familiar. This is what the universe we think looks like when we look at it on very large scales. So we can simulate now realistic universes spanning a huge number of orders of magnitude. So we are able to simulate the universe on those very large scales, but also to zoom in and to simulate the galaxies themselves, their shapes, the energetic processes that happen inside galaxies. So at the end of the day, these simulations are now playing a crucial and key role in how we interpret our observations, right? Because what we do in cosmology today is we run these very, very big and complex simulations and compare their output with our observations. We cannot do, solve our models by hand with pen and paper. This is not possible anymore since at least 20 years or so. So the question that I'm interested in now in my research is to what extent we can automate the analysis and interpretation of cosmological data, including observational and simulation data. And beyond that question, not only analysis and interpretation, but can we also automate the step of hypothesis generation? Okay, so if you give me some data, can I also try to think of AI systems that come up with new questions about the data? So this falls into those concepts of self-driving laboratories and the new field of autonomous scientific discovery. The concept of self-driving laboratories is not new. If you look in the literature, there are some papers that date back at least 20 years or so, like this paper from Nature in 2004. And if you read the description here, it's almost, the exact same words and ideas that are employed in what Google and Meta are coming up with in recent months in this field of AI scientists, etc. So the key image on this slide is this loop here of robo-scientist hypothesis generation and experiment loop. And what has become clear since maybe a year or two is that we can implement this loop not with mechanical robots, but in my case with large language models or large multimodal models that play the role of the robot. And the class of systems that I am building with those foundation models is called multi-agent systems, and you will understand why it's called like that. But before we go into describing the system, let's go back to the sort of research I want to automate. So what does a cosmological data analysis look like? It always starts with some data. So in the case that I'm going to show here for a bit of the presentation, the data we are interested in is a map of the gravitational lensing of the cosmic microwave background. So it made the news last year. And this, first, the cosmic microwave background is the oldest light in the universe. It comes from 14 billion years away from today, from the Big Bang. And it looks like that. This image is certainly familiar to some of you. And on its path from the Big Bang to us, these photons that you see illustrated in blue here are interacting with the large-scale structure that is forming, which was what we looked at in the simulation. And that is illustrated by this purple color here. The main interaction between the CMB photons, the cosmic microwave background photons, and matter is the gravitational interaction. It is called gravitational lensing, and this is the effect that bends the light rays, okay, just due to the gravitational potential. With telescopes such as my favorite telescope, the Atacama Cosmology telescope, we can measure the CMB and extract the lensing effect very, very accurately. This is, so we use, very complex data processing pipelines to go from our raw observations of the photons that fall into our telescope to this extracted map of the CMB lensing, or which is synonym to the map of the dark matter. Is there any question on this? Okay. So this data is huge, as I said. The raw volume of data for the survey that we have with this telescope is of the order of 100 terabytes. We cannot analyze it all at once. So what we do is that we take some sort of data compression steps before we try to understand how this data is compatible with theoretical models. And the main compression tool that we use in cosmology today is called the power spectrum, and it corresponds to taking a sort of Fourier transform of this map. For those that are more familiar with these tools, it's actually called the spherical harmonic transform. And at the end of the day, the data that I am going to focus on for this part of the presentation is actually very small and is only these 10 data points in the blue area of this graph. Okay, so there are 10 red data points. And this is the data that we want to try to explain with our favorite cosmological model. So we have the data and we have a model, and the model makes a prediction, and the prediction that the best model makes is in black here. And it fits very well. So how do we compare data and model? We work within the framework of Bayesian inference. So we try to solve the inverse problem, which is that if there is some data here, what's the model that explains it best? Solving this problem within Bayesian inference amounts to solving this equation, the Bayes theorem, where there are two important pieces of information, D, the data, and theta, the model parameters. And P represents the posterior, well, the probability distribution. So our goal, when we solve the inverse problem, is to compute the left-hand side of this equation, which gives us the probability of the model given the data that is observed. Okay? The result is very nice. You can then put it in a table like Wikipedia does, and you get things like this. So on this table, you see the main parameters of our model, and on the right column, you see measured values, which correspond to a mean value and the standard deviation. So that's just the outcome of this probability distribution on the parameter given the data. Okay? When I look at it for parameter by parameter. And in fact, if you look a bit more closely, this model only has 6 independent parameters, the first rows, and the rest can be computed as derived parameters. So the right column here, we call it parameter constraints, or constraints on the cosmological parameters. So most of this is going to be cryptic to many of you, but we don't really care about trying to understand each of these parameters for today. But some of these parameters, at least you, I'm sure, are familiar with. For instance, one of those, let me see if I have put some markers. Yeah. For instance, this row here, age of the universe, you see, 13.7 plus or minus 0.02 billion years. So this is the age of the universe. We can compute it from these 6 parameters. There are other parameters that will be familiar, maybe the dark energy density parameter, omega lambda, 0.68. So that's the fraction of dark energy in the universe. And that corresponds to this 70%, right? 0.68 is like 0.70. And the dark matter fraction, the ordinary matter fraction, which also corresponds to some rewriting of those. So it's really from this sort of data, as I have shown, that today in cosmology we can say what the universe is made of, how old it is, etc. So these analyses are very fun to do. So we want to estimate the left-hand side of this equation here, which is P of, we have problems with this pointer, P of parameter given data. And it's actually not very difficult to solve. The key piece here that we need to compute is the probability of data given the model parameter. It is called the likelihood. Okay, and we can compute this piece very simply using a simulation or a simple numerical solver in my case. We have two software packages typically to use to compute this term here. And the main one is called the Kavli. It's developed by Anthony Lewis. And you see by looking at the citations that this paper has accumulated, is just the paper that presented this software, that it is actually in almost every cosmology CMB paper that comes out. This is used everywhere, this software. Another one is called Class. It's doing the same, but instead of being written in with a Fortran backend, it has a C language backend. And it is a bit more recent, but also accumulates almost all citations from all cosmology papers. So this tells us how to compute essentially that term in the right-hand side. And I also need to estimate the probability or to sample the parameter space. And to do that, we use Monte Carlo Markov chains. So this corresponds to essentially doing a random walk in the parameter space guided by our data. You see an illustration here of such random walk, where we are exploring here different parameter values as a function of steps in the chain. We also use for this in my field in cosmology, we use a software package called Cobaya, also developed by Anthony Lewis. And I should say, if you are interested in software, that Anthony Lewis is not only a cosmologist, but also the main lead inventor and developer of something called Word Web, which is a thesaurus for dictionaries, and of crossword compiler, which is what I think some big newspapers like Guardian or maybe even New York Times, or I forgot which one, are using to program their crossword games. So it's not a surprise that he's actually the developer of most of the software we use in my field. So we solved that step with his package, and after our random walk, we can collect all of these values that were explored and put them in an histogram. And that's when I read this histogram here that I can say which is the mean value of the parameter and the standard deviation. In fact, before being able to extract that final piece of information, what I can just do is to fit a probability distribution to this histogram. It is called kernel density estimation. So the illustration in 1D here shows you how I go from my samples to mean and standard deviation value or parameter constraints, which I can then put in the Wikipedia table. But you can also do that in 2D or in 10D or in however many parameter dimension you want. And in 2D, when you project in 2 dimensions with 2 parameters, the posterior probability distribution looks like that. Okay, on the right here. And these contours here are contours of constant probability. The middle one tells us the 1 sigma confidence level interval, and the further one gives us the 2 sigma or 95% confidence level interval. This is also done with a software package developed by Anthony Lewis. So now let's go back to our data. We have 10 data points, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we want to fit our model, the black line, to this data and tell what are the cosmological parameter constraints. So we did that exactly 1 year ago in a paper that was published in an astrophysics journal. And the result that you see here now, it looks familiar. It's this posterior probability distribution. The contours also show you the 68 and 95 confidence level region. If you look closely, you even recognize some parameters that are now familiar, like the matter fraction or the famous Hubble constant parameter, which is another way of writing the age of the universe. So this was is maybe one of the most important results in CMB cosmology of the last year or two. And this was led by our group in Cambridge. Maybe many of you know Professor Sherwin here in the tent. And that led this analysis. So when I started to become aware that large language models are going to play a very important role in science, it was around the same time as we were finishing our work on this, and this seemed to be like the perfect playground to test some automation. So can we automate this? Here is some evaluation results on some coding data set of the most recent large language or large multimodal models produced by the industry. And the one that stood out in May last year was GPT-4o. And this is what I then started to work with in my system. So the multi-agent system is called CMB agent. It is presented in this archive preprint, and the code is available on GitHub. So here, and public, so there is all our source code. And the idea is, is inspired from things that were being produced last year, and in particular by a team at Microsoft that then separated from Microsoft. So the original software that they developed is called AutoGen, and then they split. And I think it's now led by someone at Google DeepMind and another person at Penn State. And it's now called AG2. So from there, we picked some ideas. The key ideas are here. That first, if I have a complex task, I will ask large language models to draw a plan and split this complicated task into many easier subtasks. We then distribute those subtasks to other large language model agents, which will, for instance, either retrieve information on the software packages that we want to use in our analysis. I have told you now about the packages developed by Anthony Lewis that are named here. And I can also program a large language model agent to write entire code pipelines. Okay, we call this agent the engineer agent. It writes the code. And once there is an agreement that the code and all the information have been generated in a satisfactory way, we can send all of this for execution, which is also carried out by another agent called the executor agent. In this first iteration of the software, CMB agent, there is a human in the loop at every step. So that means that we are using this system as an assistant, and we give feedback every time some information is generated by the large language models. We check it and we decide who to handle the next task to, okay? Here is an example of a plan once it has been designed after some round of feedbacks with the user. So our task is to derive the cosmological parameter constraints from ACT-DR6 CMB lensing data. I think now you can understand what I mean by that. And this main task was broken into 5 steps, each step being carried out by a different large language model agent. If you take a step back and look at the system architecture, from a broader view, what happens is that there is first a round of a conversation between the human user, and the planner, which designs the plan. Then we retrieve information from either, related to the data we want to use, here the CMB lensing data from ACT, or how we should handle and manipulate the software packages that are in blue here. And once all of this is retrieved, we send to engineer, which writes the Python code, and then send for execution to the executor. We were able to reanalyze the CMB lensing data very fast, within like 10 minutes using this system, without writing a single line of codes for the parameter inference pipeline. Okay, so with this large language model multi-agent system assistant, we were able to recover, as you can see in red here on this plot, the parameter constraints that were published by our ACT collaboration, which are in blue here. So this exercise would certainly have taken around a full day of work to even an experienced cosmologist, because you have to go on the server where the data is, retrieve the data, remember how to use the codes, etc., and set up everything, run the chains, etc. So it's very time consuming. And I am now convinced that all of this is something of the past very soon, because it will be fully automated. So all the codes are public. You can look at them there. If you want to look at this reproduction analysis, you can also check or read the docs, reproducing ACT-DR6 lensing analysis. And here you will see how the plan is designed, and everything that says admin in yellow is something I have inputted by hand in the workflow myself. So I typed by hand to ask some updates on what's being done. Okay. So you can see here we run the MCMC. The MCMC chains are here. We set up the MCMC chain, and then we run the Markov chain analysis. The download of the original chain is also done in natural language. The agents have some information on where to find the chains, etc. So all of this pipeline is reproduced in essentially natural language with this multi-agent system assistant. So that's the picture. I think, was there some question? Yeah. When the CMB agent automatically produced those results, what was the steps in which the human was involved in correcting feedback? So it's all the yellow steps in this documentation, and there is, a number of those. But if you look closely at those feedback, it's very basic stuff that we ask to the LLM to update. And in fact, now it's very clear we can completely take the human out of this loop and do everything automatically, as I will show you. So we have added a few things since December. We have implemented, yes?
So we have software agent and research software agent and coding agent, and all of them feel like doing similar things. Is there a reason why it needs to separate them?
Yes, so the research software agent is specialized. So in green here on this circle, what we call software agent are LLM agents that have been given instruction on how to use very well-established software packages that the entire community uses. And in purple, we have tried to implement agents to use research software, but to use software packages that are being developed, actively at this time. And two examples are the software that we, myself and my colleague Inigo Zubeldia are developing here in Cambridge. There is very sparse documentation, okay? And things are not, very stable, etc. And we were wanting to ask, are these systems also useful in handling those software? And the answer seems to be yes, definitely. The coder agents, they don't do any form of retrieval augmented generation. Okay, so what makes this software, this purple and blue circles here particular is because they have documents, they have a database in which they can look for information. So we do this with vector embeddings on the OpenAI platform as of now. And all of these agents, they have a vector store of documents attached that they can perform a RAG on, retrieval augmented generation. Okay? So the new addition is that we have implemented at the end of each session a step of summarizing what we have done and saving these summaries of what we have done, including the feedback and updates, into a database of session summaries. So that when we start a new session with the system, we have a memory agent which will do RAG, which will do retrieval on those summaries to try to reach a solution that's more optimal in a quicker way. We also have started to break down each of these agents in many smaller multi-agent systems. So now the plan is not designed just by one planner agent, but by a collaboration between 2 or 3 LLMs that one will suggest a plan, the other one will provide criticism on the suggestion, and so you can make the plan evolve without human feedback, okay? We also use structured outputs so that the generated text from the LLMs is well structured into, JSON format, if you like, or dictionaries. And we now heavily rely on multi-large language models, meaning we don't just use GPT-4o. For coding, we tend to use Claude, for instance, or Gemini and other models. And we also implement this or use this new AG2, so from this software here, a Swarm framework, which allows us to program the transitions between this agent on the basis of function calls. That allows us now to completely take the human out of this loop, and that's where it's becoming interesting. So let's try to demonstrate how things work with a recent task that I was working on. I will first, yeah, I think it's instructive to show first a simple exercise. So yes, this was interesting. So here, this here is really not CMB agent, it's just what, for instance, AG2, this software that I rely on, can allow you to do. So in this example, we have a joker, some response formatting agent which will format the response from the joker agent, and then a critic which will provide criticism on the joke to try to improve it. This is exactly the same idea as we use for developing a plan. Okay, except here we develop a joke. So yeah, let's run all of this. So I can, here everything will be automated. The Joker agent knows that after it has to send to the Joker response formatter, which then has to send to the critic, and the critic has then to send back to the Joker. So it goes around like that. So here it has made first reminded us what it wants to do. It comes up with a joke and an explanation. This is then critiqued, and we collect some recommendation to improve the joke. So in this case, for instance, we use a conversation between a model from OpenAI called O3 and GPT-4o from OpenAI, and Claude from Anthropic that provides the criticisms. So all of this has a cost, which is proportional to the number of prompt and completion tokens. And for instance, this step here costed 1 cent. So if you let this go, at the end you can write a joke or write an entire book or do anything you would like. You understand the idea. We can move on to less fun things. So I think the other one that's maybe very instructive is this one. So, I also teach in this data intensive science masters, and I have to develop lectures. And each time, I make new material, it's good to ask my course director some feedback on whether, he thinks the lecture is well fitted for the MPhil program. So here I programmed myself as a lecturer agent, and I programmed James Ferguson as the course director agent. So if you look, at the message of the course director, let's see. See, you make recommendation to improve the lecture plan, etc. You must ensure the level of knowledge is fine, etc. So we will run this. So here there is some feedback that is gonna be, I have set a loop of feedback and limited it to have 2 rounds of feedback. And once these 2 rounds of feedback have been performed, the main task is to prepare this lecture on neural network. When these 2 rounds of feedback have been performed, I will switch to an agent or another part of the multi-agent system here, where we will produce the course material, including the lecture notes and the plots for the lectures. Okay? So it has come up with a plan for the lecture. I'm always kind of mind blown at, actually the quality of what's coming out of this. I think this is going to have a huge impact, not only in research, but also in teaching. For instance, here, it's very likely that, you know, here I spent, what, 2 hours programming that, and I think next year, when for the second iteration of my course, I will certainly rely quite a bit on something like that. So now we have no more feedback left for the lecture plan. You see, it says, even comments on whether the plan is good. That's our final lecture plan. And yeah, there is more than I would have thought about this topic, which I have taught last year also without LLMs. So now I think what's going to happen is that the engineer will write some code to produce either some plots or even some lecture notes. We will see. So here, what's happening here is I have an output directory, and you should see things appearing here, automatically generated by the system.
There's one question that asks, how do you define when to stop this process?
Yeah, so there is the question on how do you come up with the optimal architecture, you know, how many rounds of feedbacks you should set, and where to stop. So in my experience, if I ask for too much feedback, it can become overly complicated. And I had one instance when it made my computer crash when it started to run the code, because, you know, it tried to run, I don't know, 500 instances of my software. And yeah, actually I had to restart the laptop. So there is a trade-off, and we are interested in exploring this systematically. How you know, where to stop, how to set up these transitions, etc. It always takes a bit of time.
Question about the sort of RAG agents, software agents. So those are you've got some kind of analytical tools,
Yes,
some calculation tools. It sounds like those are sort of wrapped by a little LLM layer, essentially. Is that right? So that it's not directly calling the tools from the sort of agent pipeline and getting results out. There's a kind of wrapper on them that's interpreting information in and out. Is that right?
yes. So let me show you exactly what the software agents do for the RAG. So for the RAG part, we have some, you know, folders here, which I give the agent access to. And for to teach them how to use the software, I just write simple tutorials like this. You know, giving some generic templates of how to set up the codes and perform computations. Do you see what?
So you're kind of teaching it how to use the tools rather than having that very direct programmatic kind of interface.
Yes.
take this data, do this to it, pass it in, take this stuff out. It's really, yeah.
Yeah, you have to teach the LLM with such documentation how to use the tool. You could take a different approach than this RAG-based approach, which is fine tuning. So there you would have to actually download the large language model locally and then train it on the task and update its actual hyperparameters. Yeah, we don't touch the large language model. We just append some context, essentially.
Yeah, I was just sort of thinking about how you plug in these other tools, whether you have to do it in this way, or whether you can do it a bit more of a direct way, if you want to use some standard analytical kind of tool in the pipeline.
Yes, so and then also what's going on here is there is some code that's written, like you see here. And then this code is executed by the executor agent. So that's run on the computer in a shell. And I think now it probably has been executed. Well, it has even trained some neural nets here, you see? So that's maybe one of the first time here where you have, maybe for some of you, you have witnessed here a neural network, which is the large language model, training another neural network. And that's pretty fun. So you see, it has made now all these plots, right? A confusion matrix, a loss function, etc. Well, it's all here, output on the screen. A timeline of neural network development. Some very nice explanation of activation functions. So why should I spend time writing lectures? Yes?
So I've got a question about the cosmological simulation of,
Yes.
and experiments. And yeah, the suggestion you're now at the point where you can take the human out of the loop. Is there anything to stop one of those agents going off the rails and saying, well, the experiment I'm going to perform is going to feed 70 terabytes of data to an LLM and blow your total budget? Yeah.
So there are some in AG2, they have, for instance, some preset pieces of strings that the LLM, if it tries to execute it, it will be stopped. Like, if it sees RM minus RF, somewhere in the code, it will actually stop and tell you there is a problem. So you can by hand implement some sort of, blocks there. Okay? So I see some people are need to leave, but yeah, I don't know. I will just run the final one as we wrap up. So the final one is I think it's this. So yeah, we will compute a cosmological observable. It may take time, but here there will be actually some RAG. So the class SE agent is gonna do RAG on the documents that I showed you here. It will essentially collect the information from this tutorial, put it in the Python code, and then this will be run, and it will actually run my class SZ software. So I will let this run. This is also now completely automatic with a round of feedback to make a nice plan to solve this task, and then run the code and show the plots and go back to the admin. So yeah, that's all I have to say. There is a lot of things that I'm sure you are now maybe thinking about, and myself as well. So this is very exciting area, and yeah, I had this kind of generic sort of vision slides, you know that now scientific discovery is about to be automated in a dramatic way, I think. The first example of that was this protein structure predictions by AlphaFold, which awarded the Nobel Prize to Google. They released a few days ago a multi-agent system to do things that are very similar to what I am working on. There was this piece of news by some scientists that mentioned using that new Google co-scientist tool, they were able to apparently solve something that took them years in 48 hours. So the next step is really the AI scientists, so generate new ideas, assess them, and implement them completely automatically. We can draw analogies with self-driving cars. And I think we are now between, maybe 3 and 4, and in a few years, it's likely we will be working with systems like that, which will just be like working with self-driving laboratories. And you can even imagine further down the road that these systems will become even more developed and available. Not only you will have, one lab, but many self-driving laboratories. And our goal as human scientists is going to be very different from what we are doing now. It's probably will look like we will have to learn how to orchestrate those tools, how to develop them. And the most challenging task, I think, is gonna be the task of understanding the output of this system, because they will rely on their own understanding of data and science, which is actually not the way we think. They work with different embeddings, these foundation models, and the challenge will be to understand. For instance, if you have a new drug that's produced, it works, it's been produced by an AI system, it works, it cures people, but you don't know how it works, it will be problematic, but you still will want to use it. This is a very hot topic, a race to power, because knowledge is power, and it's also, I think, a paradigm change that we are now witnessing, where humans are no longer at the center of production of knowledge. And yeah, that's all I have to say. Thanks a lot.